Hi, dear students, you are watching Study with Sheraz, and in today's lecture, we are going to talk about the Wilson cloud chamber. Basically, we have started the detection and measurement of the radioactivity, and in the previous lecture, we discussed about the photographic method and that of the GM counter for the detection and measurement of radioactivity. If you people have not watched that lecture, the link of that lecture is given in the description section and the video is present at the end screen. So you must watch that video in order to get the idea of the detection and measurement of the radioactivity. So in today's lecture we are going to start with the Wilson cloud chamber and then we will discuss about the scintillation counter. So this is basically the construction of the Wilson cloud chamber based upon the phenomena of the ionization. So it's also an ionization chamber. It uses the method of the ionization to study the properties of the radiations. So first of all, we will talk about the construction of the Wilson cloud chamber, then we will talk about the functioning, and then we will talk about its merits and demerits. So first of all, it consists of a metallic chamber. This chamber is provided by a glass window at the top in order to view the inside of the chamber. Here is also a glass window that is for the entry of the radiations. So this is present the vacuum chamber in order to produce the high vacuum inside the Wilson cloud chamber. This is a piston that is provided with a metallic plate, and on the top of this plate there is present a velvet pad that is soaked with the alcohol and water. The apparatus is provided by a source of potential. The lining of the chamber acts as the anode, whereas the piston is acting as the cathode. So this is done to provide electric field between the inside the chamber. So if we talk about the working of the velvet pad that is present on the plate is soaked in the mixture of the water and alcohol, and these substances vaporize inside of the chamber and saturate the inner atmosphere of the chamber. So whenever radiations enter into the Wilson cloud chamber from the window, the piston is drawn down, and drawing down of the piston creates low pressure inside the chamber, and it causes the supersaturation of the vapors of alcohol and water. Whenever radiations enter into the space of the Wilson cloud chamber, they cause ionization. So ions are produced in the Wilson cloud chamber, and these ions act as a place or act as a site for the condensation of the supersaturated vapors of the alcohol and water. So these vapors condense on the ions, and the condensation of these vapors of water and alcohol produce the cloudy tracks within the Wilson cloud chambers, and these tracks can be viewed by illuminating the inside of the chamber, and this is a camera which can take the photograph of the cloudy tracks for the use in future and for the further analysis of the radiations. So this is all about the working of the Wilson cloud chamber. If we talk about how does the cloudy tracks look like, so if alpha radiations are being entered in the Wilson cloud chamber, so this type of the tracks are produced. These are the straight lines moving through the Wilson cloud chamber. If beta radiations are used, so irregular tracks are produced. If gamma radiations are used in the Wilson cloud chamber, there is no pattern of the cloudy tracks. These are completely irregular. These are very short and completely irregular. So the most regular and long tracks are produced by the alpha radiations. Somewhat irregular are produced by beta radiations, and completely irregular and without any pattern are produced by the gamma radiation. It shows that the alpha radiations cause the most ionization, whereas the gamma radiations cause the least ionization. And these tracks show that we can differentiate between various types of the radiation by using Wilson cloud chamber. This was the disadvantage of the GM counter, that it cannot differentiate between various types of the radiations. But Wilson cloud chamber can differentiate between various types of the radiations based upon the shape of their tracks. So this can be written as an advantage of the Wilson cloud chamber. If we talk about the disadvantage of, first of all, it's not possible to build such a large Wilson cloud chamber that can show the long or whole path of the radiations, because the radiations are moving very fast. So Wilson cloud chambers are very small as compared to that of the path of the radiations. So no long tracks can be produced because the size of Wilson cloud chamber is much small. The second disadvantage of the Wilson cloud chamber is that the supersaturation is only for a short period of time. So if the radiations are made to enter in the Wilson cloud chamber a bit late as compared to that of the supersaturation, no tracks would be produced. Next we talk about the scintillation method or the scintillation counter. So first of all, important that what is scintillator? Scintillator is a substance that emits flash of light when it is struck by a high speed radiation, mostly gamma radiations. And these may be like the activated sodium iodide crystals. So these are the substances that produce flash of light when they are struck by a high energy radiation, and that radiation may be a gamma radiation, and scintillation counters are mostly used for the detection and measurement of the gamma radiation. So here is a schematic diagram of the scintillation counter, in which it's provided with a scintillator. Inside the scintillator there is a photocathode, and both of these are optically coupled with each other. The next is the photomultiplier tube that can increase or multiply the number of the photoelectrons. Then there is an electron counting system that can produce pulses of current for each of the photoelectron. So radiations are made to fall on the scintillator, just like the sodium iodide crystal. So it would produce a flash of light when it is struck by the radiation, and this flash of light can excite and knock out an electron in the photocathode. Whenever an electron is released from the photocathode, next are the almost 10 positively charged plates of the photomultiplier tube. So these positively charged plates withdraw the electron from the photocathode, from the surface of photocathode, and they, because these are positively charged, they can give extra kinetic energy to the electron. And whenever that first photoelectron would strike on the surface of first anode plate, it would produce another electron. So there would be total 2 electrons that would be moving in the photomultiplier tube. The second positively charged plate would attract the 2 electrons, giving them extra potential, because the potential is increasing when we move from first plate to the 10th plate. So as the electrons are moving forward, the positive potential is increasing, their kinetic energy is increasing. So in this way 3 electron, 4 electron, up to 10 electrons would be produced by the positively charged photomultiplier plates. And at the end, the counting system would count 10 electrons for each of the flash of radiation. But the pulses that are produced here at the electron counting system are proportional to the energy of the radiation that was absorbed or that was reflected by the scintillator tube. So size of the pulse is proportional to the energy of the radiation absorbed. So this is one of the best advantage of the photomultiplier tube and scintillation counter, that the energy or the size of pulse is proportional to the energy of the radiation used. So this was all about the detection and measurement of radiation and radioactivity. We will meet in the next video. Up till then, Allah Hafiz.